All right. All right. Hello, everyone. This is the lecture for section 3.1, defining the derivative. So first of all, I want to start out by requesting that if you can, for this section, be able to have your phone free or have at least a second screen so that you guys can follow along on some calculators that are going to be able to pop up on your phone. I've got some QR codes on the way down and some links to Desmos calculators. That'll be real beneficial for you in doing your homework and in doing the lecture questions and doing the quick checks, okay? So now, in section 2.2, 2.3, and 2.4, we got the idea of a limit, okay? We're gonna use that definition of a limit to help us define the biggest portion of Calc 1, the derivative, okay? So we're going to get a real good definition of it. We'll build up to it geometrically, okay? And then after we get the definition of a limit, we're going to go ahead and start sticking it into some real life applications, okay? So the first thing I want to define is this idea of a secant line, okay? So a secant line, right, is just a line that connects 2 points on a graph, okay? In particular, what we're going to be looking at is the slope of that secant line, okay? And this is exactly how you would think it was from pre-calc or algebra or high school, okay? It's your y2 minus y1 over x2 minus x1, okay? There's an equivalent explanation or an equivalent formulation of the slope of a secant line, and it's this one right here, okay? And this is over some interval a comma a plus h, okay? Both of these are equivalent explanations for the slope of a secant line, but they differ in just a little way. So I want to show you guys what both of them really look like, okay? So like I said, I like pictures. So let's go ahead and I'm going to go ahead and graph a function here. I'm going to go ahead and do a swoosh here like that. So let's say this is my function f, okay? What I'm going to do for this one is going to be the yellow one, the very first one, okay? So for this one, I'm going to go ahead and choose out my 2 points. This is going to be my a, and this is going to be my f of a, right? So then this point right here would be a comma f of a, right? I'm going to choose another point way out here, a value x. So this is going to have a point here. And the output for this is also going to be f of x, right? So then this point would be x comma f of x. Okay. And like I said, I get to connect these 2 points. So I can connect these 2 points just like this. And I'm going to have a line that goes straight through, correct? There we go. There's my line. Okay. And in particular, like I said, what I want to really concentrate on is the slope of this line, right? And it's exactly how you would think we would need to compute it. It's going to be my y2 minus y1 over x2 minus x1. So f of x minus f of a all over x minus a. That is the slope of that line. Okay. So now on the square on the right, I'm going to do this one. Make that highlighter a little thicker. There you go. I'm going to do this one. It's going to be the one in the blue. Okay. It's got the same formulation with an added twist. Okay. So let me go ahead and do my function. Here's my function f, right? I'm going to choose my 2 points. I'm going to choose them in a specific way. I'm going to grab this point. This is still going to be a, which means my output is going to be f of a, right? Okay. But now what I want to do is this. I'm going to go ahead and define a distance here. This is going to be my distance h. And I'm going to choose my second point up here based off of this distance right here. This is now going to be a plus h. Since I'm adding h to a, that's my a plus h, okay? This point right here has to have an output. And we know that's going to be f of a plus h. So this point right here is now a plus h, comma, f of a plus h. Okay, I am still going to connect the points. Now I'm trying to connect. There we go. Oh. There we go. All right. I get to still connect those 2 points, right? This point over here is still a comma f of a. Again, all I'm going to do here is compute the slope of that line, and that is going to be just how you think it'd be. M is equal to my y2 f of a plus h minus f of a all over h if you simplify it all down. Okay, so both of these are slopes of the secant line. Okay, one of them, the one on the left, is specifically found by 2 points. Okay, and then the one on the right is defined by the 1 point plus a distance. There's your difference. There's the difference between the two. Okay, both of these are completely valid. Okay, now for the rest of the course, I am going to be using the definition that is on the right. Okay, it turns out it's the understanding behind the derivative is much simpler, I believe, by doing it with the one on the right. You can do the stuff with the same stuff with the one on the left. It's up to you. Okay, so what I want to do now is to get you guys some practice with this. Is we're going to go ahead and find the equation of the secant line. Okay, for a specific function at a point 2 with that distance h being 5. Okay, that means that I'm looking for the slope or the equation of a line between 2 comma 2.5, that 0.5 being this h that I'm adding. Okay, so if I want to find the equation of a secant line, this is still an equation of a line. So I'm looking for a y equals mx plus b. Okay, so that means I need to find 2 things. I need to find my m, I need to find my b, and that's our game plan here. We're going to try to do the first one first, and the second one second. Okay, so for 1, I need to find m, right? That means I need to find f of 2 and f of 2.5. So f of 2, if we compute that out, that's going to be 2 squared plus 2, and that's going to be 6. Yes, 6. And the 2.5 is going to be 2.5 squared plus 2.5. And this is going to be 8.75. Okay. We have everything we need now. Okay. So we can go ahead and do it. M is equal to my f of, if you want to call it something here, let's do x2, x1, right? So this is going to be f of x2 minus f of x1 all over x2 minus x1. So my x2 was the 8.75 minus 6 for my f1, f of x1, and this is going to be 2.5 minus 2. This reduces down to 2.75 over 0.5, and this is 5.5. So we have just found m. We have just found our slope. Okay. The next thing we have to do now is we need to find our b. We need to find our y-intercept. So if you guys recall from pre-calc, okay, we have this. We have y is equal to, we know what m is, 5.5x plus b. Okay, we get to use one of our points, one of these 2 points. I'm going to go ahead and use the simpler one, right? And it has to go through 2, 6. That's what this one gives us. So let's go ahead and compute that now. We know what x is, we know what y is. So it's going to be 6 is equal to 5.5 times 2 plus b, right? 6 is equal to 5.5 times 2, that is 11. Plus b, this tells us that b has to equal -5. And we are done. This is our b. So then therefore, the equation of my line, y is equal to 5.5x minus 5, and we are done. Okay. So what comes up next here is quick checks for everybody to try. Make sure you go ahead, turn these into your discussion groups. I'll be grabbing some from there for to complete our notes. So everybody has answers to all of these. I want to keep going. The next thing I want to define now that we know what a tangent line is, or sorry, now that we know what a secant line is that now I want to define a tangent line. Okay, this is the much more important definition. The idea of a tangent line. Okay, it is a line that passes through a point a comma f of a that has the same slope as f. Okay, so what does that mean? I'm going to go ahead and draw my function again. Okay, here's my function. Okay, here's f. And I'm going to choose a point right here. This is going to be my point A, right? And it's going to have my output f of a. Okay. The idea behind the tangent line is it's a line that basically hugs that point only at that point. Okay. So let me go ahead and do a line. This is going to be real trippy. I'm going to try to do this as best as possible. Something like this. My computer's being a little glitchy here. I'm trying. There we go. There we go. Right there. So it's a point that sort of hugs. It's a line that sort of hugs that point exactly right there. Exactly right there. Okay. And this is what we're going to call the tangent line right here. This is our tangent line. Okay. Graphically, okay, what we're trying to do when we try to find a derivative is we're trying to find the slope of that tangent line. We're trying to find the slope exactly at a point. Okay. In other words, we're trying to find the instantaneous rate of change. Okay. So to show you guys what I'm talking about here, this is one of the first sections where I hope everybody has at least a second screen or a cell phone. This has got a QR code that I want everybody to scan on your phone. It opens up a Desmos calculator that I've prepared for everybody to use. You can use it on your homeworks. That'll sort of allow you to compute this stuff without having to do it all by hand, okay? So what I'm gonna do, I'm gonna show you guys the example here, okay, is we're gonna go ahead and compute estimate the slope of the tangent line for a point x equal 2 for the function x squared plus x. Okay, so thankfully I have it open on a separate web browser. Okay, so the first thing I'm going to do is I'm going to change the equation so it's the one that I need. It's going to be x squared plus x. Okay, so notice that the m that's here, it is computing the slope. Okay, let me go ahead and do a double screen here. There we go. Okay, so first thing I want to do is I want to go ahead and move, if you guys notice, it's asking us for x equal 2. That's going to be our a. So I'm going to move this to 2. There we go. Okay. What I want everybody to see first is I'm going to notice that I'm using my h, so the distance, right? If I make that 0 to find my distance, to find the slope of that tangent line right there, it's telling me it's undefined. It's telling me it is undefined. I cannot find it. Okay. But what we can do, if you look, is we can back off a little bit from it. Okay. And it gives us a slope. Okay. So what we're going to do is we're going to estimate the slope of the tangent line using slopes of secant lines. And the secant lines that we're doing, we're getting them closer and closer and closer to the point that we want, x equal 2. Okay. So specifically, let's go ahead and do 1.6. So from 2 to 1.6, that is going to be a negative 0.4. Okay, so our slope here is going to be 4.6. Okay, 1.7, that's going to be negative 0.3, 4.7. The next one is 4.8. The next one after that is 4.9. So notice what's happening. We are getting secant lines. I'm zooming in on the graph. We are getting secant lines, right? Where the second point is getting closer and closer to x equal 2 from the left. Now let's go ahead and do from the right. So 2.4, that's going to be 0.4 above. So I'm going to switch this over to over here. So 5.4 is the first one. The next one down after that is 5.3. The next one after that, 5.2. The next one after that, 5.1. So hopefully everybody sees what I'm trying to do here. We're basically doing the idea of a limit, right? With the slopes of the tangent lines now, or the slopes of the secant lines, okay? So if we fix the point at 2 and we move the other one toward 2 from the left and toward 2 from the right, we get these secant lines. We get these slopes for the secant lines, okay? And if you look, the x values, just like we were doing in the limit, are getting closer to 2 from both positive and the negative side. And just how we want, they're getting close to something here, right? So looking at both of these, it looks like the slope of our tangent line has got to be something about 5, okay? Even though, right, it's a does not exist, okay? The calculator showed it to us that it's going to be a does not exist, but the slopes, they are approaching a value 5, okay? So now that you guys have this understanding, I want you guys to go into your quick check groups. Go ahead and try the one out, the one problem that's assigned to you, and see what you get. Okay. discuss them in your discussion groups, and I'll be checking on your answers. Okay, and I'll choose some out for our notes. Okay, so moving on. Now we have enough for the definition of a derivative. Okay, and I'm going to do both to show both. However, I'm going to be using the one on the right-hand side, okay, for the rest of the class. Okay, I'm going to define both. It's nothing that we haven't seen before. So let's go ahead and write these down. So the derivative is the slope of a tangent line, or the instantaneous rate of change at a point x equal a. Okay, and it is denoted using this method right here, the little prime or a little asterisk in front of f. Whenever you do the derivative, this is how you would denote it. Okay, and so let me go ahead and define both of the geometric interpretations of it. Okay, it starts out the same way that I did before. Here is my function f. Okay, here's f. I get to choose my 2 points. Okay, this is going to be a. This is going to be f of a. Okay, this point over here is x. This point over here is f of x. Okay, I can go ahead and draw this line through the 2 points. Right? Okay, so we know that this right here has a slope m equal, right, f of x minus f of a all over x minus a. We know that that's the slope. Okay, and note that that is the same as this bit right here. Okay, now comes the idea that we were doing in a previous quick check just now. We are grabbing our x value, we're grabbing this value, right? Which means we are grabbing this point and we are dragging it down toward here. Okay, and in doing so, right, the tangent line or the secant line changes. It starts getting closer and closer to x equal a, right? And if, as you would think, right, when we do that, we start getting an approximation closer and closer and closer to our tangent line. Hence the reason why this is the definition for the derivative. Okay. So now I'm going to do the one on the right-hand side. This one's the one that I'm going to use on a regular basis for the class. Same idea. So here's my function. Okay. I'm going to choose a point A. The output is f of a. I get to define this other point based off of a distance h. So this is going to be a plus h, right? And this is going to be the output a plus h. So this line has the same slope as the one that we saw above. I'm trying, you guys. There we go. It has the same slope as the one that we have above. So m is f of a plus h minus f of a all over h. That is the slope of that tangent line. That is the slope of that secant line. And notice it is the same thing here. Okay, but now look at what's happening. This is telling me that h is going to 0. So this is telling me that this distance right here, that distance, this distance right here is heading towards 0. I am making this distance smaller and smaller and smaller. I am making it go towards 0. That is grabbing this point and dragging it all the way down to this other point. Okay, that is the definition of the derivatives. Notice that both the one on the left and the one on the right are doing exactly the same thing. They're dragging one point toward A, right? It's just doing it in different styles. The first one is physically grabbing a point, dragging it over, okay? And the one on the right is making a distance go to 0, okay? So what I want to do now is I want to show you guys how to compute these, okay? And that is the next example. Okay, we're going to go ahead and algebraically find the derivative at the point x equal 2. Okay. So if you guys recall from a previous example, we estimated this already. We got 5, okay, using the secant lines from before and the secant lines from after. Okay. So if we do this process correctly, we should get at the very end, we should get 5. Okay, so let me go ahead and do this. Okay, so what we're trying to find is f prime of 2, which according to our definition is the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. Okay, notice this gives us the same problem that we got from chapter 2. We can't directly plug in h equals 0 because if we do, we divide by 0. So we can't do that. So we are going to hope that something on the top helps us cancel out that h on the bottom. Okay, and so we're just going to go ahead and do this. We're going to go ahead and follow our nose. So f of 2 plus h means I have to plug in f of 2 plus h in here. So it's going to be the limit as h approaches 0 of 2 plus h squared plus 2 plus h minus f of 2, which is going to be 2 squared plus 2 all over h. Nothing's happened yet, so let's keep going. So limit as h approaches 0. We haven't been able to take care of the limit yet, so I'm going to rewrite it again. This is going to be 4 plus 4h plus h squared. Make sure you distribute this properly, okay? Plus 2 plus h minus 4 plus 2 is 6 all over h. Okay, let's go ahead, clean up that. The limit as h approaches 0. We have a 4 and a 2, that's going to be 6. We have a 4h and an h, so plus 5h plus h squared minus 6 all over h. Okay, automatically we can see that our minus 6 from the tail cancels out a plus 6 from the front. We get left with limit as h approaches 0, 5h plus h squared all over h. Hopefully you guys see what's going on next. Limit as h approaches 0. The top has h's all across them all. So I can factor out an h and I get left with 5 plus h all over h. And now look what happens. We get rid of our problem, which is equal to the limit as h approaches 0 of 5 plus h. 5 plus 0, 5. We are done. So notice the sort of like the game plan for finding the derivative for this function at a point x equal 2. Okay, we need to go to that formula, the limit formula, the limit definition. Okay, we can't plug in 0 at the very beginning because it'll make us divide by 0. So we do everything we can to eliminate that h on the bottom. Okay, and at the end we get 5, just how we were supposed to get it at the just how we got it in our example from before. Okay, so what comes up next is I'm going to have you guys compute some of the slopes of the tangent lines for the examples that you estimated before. Okay, and they should work out the same way. Okay, so I'm going to let you guys try those out. I'm going to go ahead and move on to our very first real life application for the derivative. Okay, so as you guys can remember, the derivative is the instantaneous rate of change of a function. Okay, and this can already be applied to specifically a physics problem. Okay, this is something that you learn in physics right here, that if you have a velocity, right, the way that you compute a velocity, okay, is the change in a distance over some time. Okay, if we use that application, if you use that definition using our mathematical notations, that is equivalent to this thing. Okay, so our v, our velocity, can be found using the slope, right, and finding the change in the distance in a position, right, over some time. Okay, so what I want to do, I'm going to go ahead and do example 4 here. Okay, so we have a bowling ball. We drop it off of a 1,000 meter cliff at the Grand Canyon. Okay, and the distance from the top of the cliff to the bowling ball, wherever the bowling ball is, right, is given by that. Okay, and I just want to find, we're going to find and interpret both of these two, S4 and S of 6. Okay, so I'm going to go ahead and draw a picture so we know what we're doing here. Okay, here is our cliff, right? And here we are up top. Right, and we are dropping this down. Okay, the distance here is 1,000 meters. Okay, so let's go ahead and do S of 4 and S of 6. It's exactly how you would think it is. So S of 4 means that we get to plug it into this thing. So minus 4.9, 4 squared plus 1,000. And if we do this, we get 421.6. Okay, so just keep in mind, right, that S is the distance and T is given by our time. So then this is saying that at 4 seconds, right, the bowling ball is 421.6 meters off the ground. Okay, S of 6 is exactly the same thing. So minus 4.96 squared plus 1,000. And if you do that appropriately, 323.6, right? So at same interpretation, 6 seconds, the bowling ball is 323.6 meters off the ground. Okay. So now we're going to go ahead and estimate how fast the ball is traveling at exactly 4 seconds. Okay. So that's going to require us to use our Desmos calculator. So I'm going to go ahead and change my equation here. It's negative 4.9 x squared, right? Plus 1,000. Okay. This might require you to zoom in and zoom out. For me, I need to zoom out a lot to right there. There we go. Okay. So we're going to estimate the speed of the ball at exactly t equal 4. So that means I'm going to put my a at 4. Okay. And I'm going to go ahead and change my h so that I can get 3, 3.5, 3.8, 3.9. Okay. So from 4 to 3, that means h is minus 1. So I'm going to go ahead and move this to minus 1. And that gives me 34.3, negative 34.3. Okay. From 4 to 3.5, that's a negative 0.5. So I'm going to move that to negative 0.5, negative 36.75. 3.8, that's going to be a negative 0.2, negative 38.22. And negative 3.9, that's going to be a negative 0.1, 38.71. Okay. I'm going to do the exact same thing from the positive side now. Okay. So from 4 to 5, that means a positive 1. So I'm going to go over to make h equal to 1. So it's going to be negative 44.1 to 4.5. That's positive 0.5. So negative 41.65. H equal 0.2. That's going to be negative 40.18. And then 4.1, negative 39.69. You write that right. Okay, so I want everybody to observe what's happening here, just like before, right? The x values are approaching 4 from both the left and the right. And we're looking at the secant lines, and they are doing something in particular too. Okay. Specifically, if we take a look at sort of 3.9 and 4.1, it looks like this is going to be 39. It looks like it's going to be 39. Okay, so that means if we calculate our derivative using our limited definition, we should get 39 somehow. Okay, so let's go ahead and do so. So we need to find f prime of 4. Right, s, we actually use s because it's an s. So it's going to be the limit as h approaches 0 of s of 4 plus h minus s of 4 all over h. Okay, let's get to it. So it's going to be the limit as h approaches 0 of negative 4.9 4 plus h squared, okay, plus 1,000 minus negative 4.94 squared plus 1,000 all over h. Okay, I'm going to go ahead and do a bit of distribution here. Okay, this negative is going to distribute to everything here, correct? So then that means that this is going to be a plus 4.9 now. And this is going to be a minus 1,000. So why did I do this for? I'm going to start cleaning stuff up here. The plus 1,000, minus 1,000, they go away. I get left with the limit as h approaches 0 of minus 4.9, 4 plus h squared plus 4.9 times 4 squared all over h. So we still have the problem. We can't plug in 0 yet. Let's go ahead and do the limit. I'm going to do equal limit. H goes to 0. Minus 4.9. I'm going to go ahead and distribute that 4 plus h squared. That's going to be 16 plus 8h plus h squared. That's h squared. Okay, plus 4.9 h 4 squared, sorry. That's going to be 16. I'm just going to go ahead and call it 16 times 16 all over h. Okay, hopefully you guys see what's going to come up now. Okay. The limit as h approaches 0 is going to be negative 78.4 plus 39.2 h minus 4.9 h squared plus 78.4. all over h. And look what happens again. A minus here, a plus here. This now reduces down to the limit as h approaches 0 of 39.2 h minus 4.9 h squared all over h. Okay, I'm going to go ahead and change this already. It has 2 h's, so I'm going to go ahead and simplify this a little bit. It's going to be h times 39.2 minus 4.9 h. And this is what takes care of our problem. Is equal to the limit as h approaches 0 of 39.2 minus 4.9 h. Now we can plug in h equals 0, and this gets us 39.2. So we estimated it using part B. We got something around 39. The actual slope of the tangent line, the instantaneous rate of change is 39.2. Okay, so now we get to actually interpret S prime of 4. Okay, so S prime of 4, I'm just going to write it out first. Prime of 4, we got the value to be 39.2. And did I screw up? I did. This is supposed to be negative. That's my bad. So this is supposed to be negative 39.2. So this is the derivative is the instantaneous rate of change, right? When we apply that to a velocity, or when we apply that to a position, right, we're saying that the derivative of the position, right, is the instantaneous rate of change in its position, aka its velocity. So what we just found is a velocity. So at exactly, right, at t equal 4 seconds, sorry, t equal 4 seconds, right? The bowling ball is moving at negative 39.2 meters per second. It is traveling at that speed. It is traveling at negative 39.2 meters per second. Okay, it makes sense that it's negative because it's moving downward. Okay, this brings us to the very first of many of your first of many results from physics, that the derivative of a position function is always going to be the velocity. Okay, and that is it for section 3.1. What's left is lecture questions. If you have any questions about the material, if you need to talk to me about these things, come visit me at my office hours. Okay, and I hope to see you guys there.